Okay, so good afternoon. This is lecture 10.2 of our group theory course. It's the second and final lecture of chapter 10, and we are going to continue to explore properties of space groups in reciprocal space. And we start by discussing the representations and characters of different groups of the wave vectors. These character tables for a variety, for basically all space groups and all distinct wave vectors, they are already tabulated, and you can find them either at this famous book by Miller and Love, Table of Irreducible Representations of Space Groups and Co-Representations of Magnetic Space Groups. But you can also find this information online on this website. Okay, so this is all well known and tabulated for all the 230 space groups. I'm going to briefly give you a flavor of how you can obtain those character tables, but as I said, this is already known. So let's consider first simorphic groups, and there is a distinction. If you remember the discussion we had last time about the group of the wave vector, if you remember the gamma point k equals to 0, the point group associated to that wave vector was the same as the point group or the rotation group, the full group factored out by the translations of the total group. This is what we call the large representation, and there's also, so large representation we usually refer to the gamma point, okay? And small representation, this is a notation. What we mean by small representation are usually groups of the wave vector of less symmetric directions in the Brillouin zone. So these are typically smaller groups. They are subgroups of the full rotation or point group of the crystal. And this is what we mean by small representation. It's usually k different than 0. Okay? So the characters for a given irreducible representation gamma I, it also carries the label k for a given k point, because for every different k point we are going to have a different group, the group of the wave vector associated to that particular k. And this is our space group symmetry operation, a point group operation R alpha, and in this case we have a simorphic group, so all the translations are translations by lattice vectors Rn. So the character is very simple. It's basically the character for the original point group multiplied by this phase factor. Okay, this complex phase factor e to the I k dot r. All right. So most of the time we are going to disregard translations. In most applications we can disregard the translations. We can factor out translations. So Rn is going to be equal to 0. So this is very simple. This will be just the characters for the rotation part or the point group part of our compound space group operation. Okay? And for large representation is the same thing. It's even simpler, because now we have k equals 0. So therefore this phase factor is already 1 for any choice of a translation vector Rn. Okay, so in this case, both the representations and the characters for this, the group of the wave vector at the gamma point are going to be identical to those that we have studied already for point groups. So this is very reasonable and simple. And let's see how it works in practice. This is one example, a simple cubic lattice, the group number 221. This is the Brillouin zone, like the gamma point at the center. The Brillouin zone is also cubic. And you have this notation for special symmetry points. Here's the X point in the middle of this face of the Brillouin zone. The R point is in the vertex of the cube, and all these different directions in the Brillouin zone. So what we do is we have to consider each K point in a separate way. So, and then we can find character tables for all the different K points. For instance, for this group, OH group, this is the character table for the gamma point, and that's why the notation here refers to the gamma point. This notation is a very old notation from the 1930s. It has some historical reasoning behind this choice of labels, but we are not going to get into that. But these are the different representations. These are all the 48 symmetry operations of the cubic group. And you can see, well, that I mean, you have one-dimensional, two-dimensional, three-dimensional representations. This group has inversion symmetry, so you can have even and odd representations under rotation. Under inversion. These are odd ones. These are even ones, and so on and so forth. So now, if you go away from the gamma point, then, for instance, this is the case for the lambda direction. The lambda direction goes from gamma to R, so is one of the 1-1-1 directions in reciprocal space. Okay, and for wave vectors along lambda, the group of the wave vector is C3V. It's a much smaller group. It has only 3 classes and 3 irreducible representations. Okay, and again, since this is a symorphic group, basically what one does is to these are simply the character table for the C3V group that we have studied before, but these choices of basis functions, they are more convenient. We're going to analyze them by the end of this lecture. They are more convenient to work with this particular problem of the group of the wave vector. So this is going to be clear by the end of this lecture. Okay, so this is a general notation for the lambda point. Is a general wave vector along the 1-1-1 direction. Okay. So this is the case for symorphic groups. For non-symorphic groups, this is slightly more complicated, but it's still very simple in the sense that the character associated to a given K point and associated to a given irreducible representation, gamma I, and for a particular space group compound operation that involves point group operation alpha and a translation tau, is going to be equal to the e to the I k dot tau, and then the character for point group operation. So the basic difference here is that for non-semorphic groups in general, tau, for some operations, tau is going to be different from 0. All right, because semorphic group will have those compound operations like screw axes and glide planes that combine point group operations with translations by vectors which have a smaller, which are smaller than the lattice vectors. So in these cases, this is going to be a non-trivial factor as long as you are away from the gamma point. If you are at the gamma point, k equals 0, so it really doesn't matter. But if you are away from the gamma point, we have to take those factors into account. Okay, and here we see again an example. This is for the diamond structure. It's a space group 227. And the Brevet lattice for the diamond structure is FCC. So you have here the same Brillouin zone as any FCC structure, right? And again, the different symmetry lines and symmetry points. Let's focus on the delta direction. The delta direction is along the one of the Cartesian coordinates kx. It goes from gamma to x. So kx different than 0 and ky kz equal to 0. This is a general notation for a wave vector at delta, along the delta direction. Okay, only the kx coordinate is different from 0. And you can see here, in this particular case, for those wave vectors at delta, the group of the wave vectors is C4V. So you see that the symmetry is reduced very much with respect to the with respect to the full group OH cubic group. Now it's C4V. And C4V has these different symmetry operations, and you can see that some of them, they are compound operations with a translation tau d. In this case, tau d is the translation that takes one atom from one sublattice in the diamond structure to the other sublattice. So it's a to the 4 1 1 1. This is the translation vector, tau d. And you see that for those compound operations, for instance, for this one and for this one, in which you have to make a translation, you see this phase factor Td here in the character table, and Td is precisely that. Is obtained, Td is actually this phase factor here. Sorry, T delta for this specific case. We're going to calculate that in more detail, but you can see already that for non-semorphic structures, it's important to take that into account. Okay, so let's talk about the characters for the equivalence representation. If you remember, in molecular applications, the equivalence representation, the characters for the equivalence representations were obtained by analyzing for the different symmetry operations how many atoms remained invariant, right, under a given symmetry operation. And this is going to be the same here with a small difference. In general, for some applications, and we are going to see that in the future, we need to define a more general equivalence representation that is specific for certain k vectors. And this is a definition of the characters for this equivalence representation. So this looks like a complicated definition, but it's actually very simple. You have an overall phase factor here. So it's specific to a given K that I'm interested into, and for a given symmetry operation, right? So that combines a translation with a rotation. So there is a phase factor, and also here this sum over J is a sum over all atoms in a unit cell, in a primitive cell to be more clear. So you sum over all atoms in a primitive cell, and you have a delta, a Kronecker delta here. So you count either 0 or 1 depending if the atom it's invariant, then you count 1, but if you move the atom to another position, you count 0. Okay, so delta Rj prime Rj is going to be 1 for Rj prime equals to Rj, and 0 otherwise, but in which Rj prime is just the result of applying a symmetry operation that combines a point group operation with a translation. You apply that to Rj, and this is Rj prime. Okay. So, but you just need to be careful, because you consider equivalent if you consider equivalency if an atom is taken to another atom in a different unit cell, but it's equivalent by a translation by a Brevet lattice vector. So you have to be careful with that, but other than that, it's a pretty straightforward definition, which is very similar to the definition that we had before. Okay, and there's another phase factor here, and Km is a reciprocal lattice vector. We are actually using this notation G, and you take into account this phase factor whenever R alpha K goes to K plus G. So if you remember, in the group of the wave vector, some symmetry operations take the wave vector not to itself, but they translate the wave vector outside the first Brillouin zone by a reciprocal lattice vector G. If that happens, then you take that into account by this phase factor. Okay, so it's slightly more complicated definition of the character for the equivalence representation, but this is going to be useful in the next few lectures. So just keep that in mind. Okay, so let's see some examples and analyze in more detail the some symmorphic space groups, and we're gonna discuss in this context the very important case of cubic lattices. There are three types of cubic Brevet lattices. One is the simple cubic, the other is the FCC, and the other is the BCC. And what I'm showing here is the reciprocal, the Brillouin zone for all these three cases. So this is the Brillouin zone for the simple cubic lattice. This is for the FCC, and this is for the BCC, with the notations for high symmetry points and directions inside the Brillouin zone. Okay. So let's look at the we have seen that before, but again, this is the character table for the cubic group, and it corresponds to the three cubic groups, the 2 to 1, 2 to 5, and 2 to 9. These are simple cubic FCC and BCC Brevet lattices, and this is for the gamma point. All right, k equals to 0. I have shown you that before. And let's see how we use this information. For instance, this character table tells me that at the gamma point I can have 3-dimensional, 2-dimensional, and 1-dimensional representation. And they can be either even or odd with respect to inversion. Okay, so this means that when I calculate a band structure, when I solve the Schrödinger equation for an electron in a crystal, then I have the energy bands. So the labels that you see here in the energy bands are precisely the labels for the irreducible representations for the group of the wave vector for each direction in the Brillouin zone. So this is an example of the energy bands for aluminum, which is an FCC structure. Again, this is the Brillouin zone, and you see here that you plot the energy bands along different directions: gamma x, x w, w l, gamma l gamma, gamma k, and kx. That corresponds to a given circuit along the first Brillouin zone. But let's focus initially on the gamma point. So what group theory is telling me is that I cannot have electronic states with degeneracy larger than 3. I can have non-degenerate, doubly degenerate, for instance gamma 1, 2, non-degenerate would, for instance, gamma 1 or gamma 2, doubly degenerate gamma 1, 2, and triply degenerate states, gamma 1, 5, gamma 2, 5, and the same for the even representations. Okay, so sorry, some of them are even here too. So there are two different notations. Sometimes you call it gamma 1 or gamma 1 plus. When you want to make to be explicit about the representation being even or odd, you use this plus or minus signs. Plus for even, minus for odd representations. Okay, so this is telling me that I cannot have degeneracies larger than 3, and this is precisely what you see. So gamma 1, it's a non-degenerate state, and it's still non-degenerate along the delta line, and it's still non-degenerate at the x point. But for instance, gamma 2, 5, what is gamma 2, 5? Gamma 2, 5 plus so this is gamma 2, 5 prime, which is also gamma 2, 5 plus. And you see that this is a 3-dimensional representation, right? So you see this state is triply degenerate, gamma 2, 5. And you see that when you go away from the gamma point, for instance, along the gamma x direction, in the delta direction, you see that this degeneracy is partially lifted. It splits into a delta 5 and a delta 2. We are going to discuss that in more detail, but this is just a consequence of the fact that the group of the wave vector along delta is smaller than the group of the wave vector at the gamma point. So we've seen that already, right? So the group of the wave vector, this is for the simple cubic, but it's the same idea. Sorry, this is it. This is for the diamond structure, not the FCC, the aluminum structure, but this is the same idea. You see that for the delta direction, I can have mostly two-dimensional representations. I must, because it's a smaller group, it's a C4V group, so I cannot have threefold degenerate states. So this is a way to understand why some degeneracies are split when I go away from the gamma point. And we are going to see that group theory tells us exactly how these different degeneracies have to be splitted. Okay? All right, so let's consider now going away from the gamma point, a certain k different from 0. And this is all tabulated for the space group 221, for instance. Space group 221 is a simple cubic. It's a simple cubic case. For space group 221, you have all the different special points and directions in the Brillouin zone and their respective symmetries, or group of the wave vector, if you want. And you see that the different character tables for all these different cases, some of them are in our textbook. Appendix C have a lot of character tables for groups of the wave vectors. Okay. And for instance, this is again the delta function. The delta direction for this particular group, the cubic group, and this is what I was telling you before. It doesn't have 3D representations, just one dimension and two-dimensional representations, and that's why the degeneracies are split when I go away from the gamma point to the delta direction. And I show this result again here. Okay. So, very good. So, what I want to discuss now, and I'm going to discuss in the next section, is what we call compatibility relation. Compatibility relation is precisely that. It tells me how the degeneracies are splitted in when I go away from high symmetry points to a lower symmetry point in the Brillouin zone. For instance, the compatibility relation between gamma 25 plus in the OH group at the gamma point must be split into delta 2 prime and delta 5. This is 1D representation. This is a 2D of space group C4V, which is the group of the wave vector for the delta direction. Okay, so this is a threefold state, threefold degenerate state. It splits into a one-fold and a two-fold degenerate bands. Okay, and this is precisely what we see here. The gamma 25 plus here, it splits into gamma 25 splits into a delta 5 and a delta 2 prime. You can't really see the prime, but it's there. Okay, so let's study that in more detail now. So compatibility relations, they tell us about the connectivity in the band structure, how I connect different points in different directions, and how I can choose the correct labels for the symmetries of the different electronic states, different band states. And in a way, it's very similar and completely analogous, actually, to something that we have already seen two, not do, which is crystal field splitting or applying strain. When you do either crystal field or you apply strain, you reduce the symmetry. You have to go from higher to lower symmetry. And what you have seen many times already here in this course is that when you do that, you take the original irreducible representation in the original group, it becomes a reducible representation in the lower symmetric group, and then you decompose it into irreducible representations of the lower symmetry group. And that's how you find out this compatibility relation. Okay? So let's do an example. Let's take the simple cubic lattice again. And I want to study compatibility relations going from gamma to the lambda direction. The lambda direction is along the main diagonal of the Brillouin zone. All right? So again, I take the group of the wave vector for the lambda direction, which is actually C3V group. And these are the character. This is the character table, and you have three irreducible representations: lambda 1, lambda 2, lambda 3. Both two of them are 1D. One of them is 2D. Okay, and these are the three different classes that you have for that group. And what you do now is you take gamma, your original symmetry or your higher symmetry position in the Brillouin zone, the gamma point, and you list all the different irreducible representations at the gamma point, the even ones and the odd ones, right, that we have seen before from the original character table of the OH group. And these are the characters. Now you decompose it. This is, again, something that we have done it many times before. So gamma 1 goes into lambda 1. Gamma 1 plus, let's use this notation. So gamma 1 plus, the totally symmetric representation, goes into lambda 1. And gamma 2 plus goes into lambda 2. Gamma 1 2 plus goes into gamma 3. And now the threefold degenerate, the 3D representations, for instance, gamma 1 5 plus, gamma 2 5 plus, they must decompose, right? So, and this one decomposes into lambda 2 and lambda 3. This one's into lambda 1 and lambda 3, and so on and so forth. So this is how you do it, okay? This is very similar to what we have done before. Another good news is that in general we don't have to do it by hand, because people in the past have taken a lot of time and have done this for us. So compatibility relations for all space groups are compiled in the literature. For instance, the Miller and Love's book that I have mentioned before. Okay, and our book has some examples for that. For instance, this is what you find in Miller and Love. This is compatibility relation for high symmetry points in the simple cubic lattice. For instance, for going from gamma to delta, or from gamma to lambda, for gamma to sigma. So along this direction, 100, 111, or 110 directions in the Brillouin zone, how each of the gamma point states how they should decompose or split their degeneracies when we go in the delta, the lambda, and the sigma directions. Okay, so these are examples of compatibility. You can also have compatibility between X and directions that go away from X, like the delta, the Z, and the S direction, and compatibility between M and directions that go away from M, which are sigma, Z, and T. Okay, so this is all done, and we can use all the results that are in the literature or in books. Okay. All right. So okay. So but there's a subtle issue here. For instance, sometimes these tables are not enough. For instance, I know that, let's take this case, gamma to 5. So I want to go from gamma to the delta direction and then back to a higher symmetry point, which is the x point. Okay, so I know that for instance, gamma to 5 plus decomposes into delta 2 prime and delta 5. So how can I find which states correspond to the symmetry states at x? So here I have the compatibility between x and delta, right? So I see here that delta 5 could either link me to x5 or to x5 prime, and delta 2 prime can take me either to x2 prime or x3. So to find exactly which states they should go into, then you have to do there are many ways to do it. You can do the compatibility directly from gamma to x and see how the gamma representations decompose into x, or you can look at the parity or the basis functions. For instance, in reality, the result here is x3 plus x5, and one way to see that is that gamma to 5 plus is even under inversion. And this is exactly, if you look at the character tables for the x point, you see that x5 it's even and x5 prime is odd under inversion. So one has to keep the same parity when going from here to here. Whenever you have groups with inversion, groups of the wave vector with inversion symmetry, then you have to keep the same parity. So you can look at the parity, or sometimes it's even equally simpler, you can look at the basis functions at the character tables. This will give us a hint on how to choose our compatible states along different points in the Brillouin zone. Okay. So looking at the basis functions takes us back into the notion of looking at atomic orbitals, because remember, S, P, and D orbitals, they have their correspondence to different basis functions. S orbitals are constants like 1, P orbitals are x, y, and z, and D orbitals are quadratic functions, right? And this is interesting because this is telling us already something about the atomic nature or the orbital character of different band states. All right. For instance, if you look at this band structure, this is a hypothetical band structure in a simple cubic crystal. We see here there is a gamma 1 plus state, and we know that gamma 1 plus is a completely symmetric structure. So most likely this is an S state. If it's lower in energy, it's most likely an S state, or some. It could also be some totally symmetric combination of different orbitals. But let's suppose it's an S state. So this is the atomic character of this state. It's S in each atom. Okay, And the compatibility tells us that gamma 1 plus goes into delta 1, and you can see that from the basis functions here. So the number 1 here, the constant, is here. So this is also S. And x1, I forgot to list here the character table for the x point, but this must also be S. And the same for lambda 1. If you go along the 1, 1, 1 direction, you see the basis function 1 is right here at the gamma 1 representation. So this band is S character for the whole Brillouin zone. Good. So now let's look at the gamma 2,5 plus. The gamma 2,5 plus, we can go back here. I don't think we have. Okay, probably this is not a good example. So this is the, so I'm gonna check that later, but I'm not sure if this is gamma 2,5 plus or gamma 2,5 minus, but this is a band with a P character, okay? So this is a triply degenerate state, meaning that this is Px, Py, and Pz. And our compatibility relations tells us that this goes into along the delta direction. This splits into delta 5 and delta 2 prime. So delta 5, you see, it's X, Y, and Z, and delta. So this is probably not correct, but I'm gonna check that later. So this is going to split between PZ and PY, since I'm going along the X direction, and the PX state here. And when I go along the lambda direction, you see lambda 1 is X plus Y plus Z. So this is a p orbital which is along the 1, 1, 1 direction. So this is, let me call it px plus py plus pz, is a linear combination of p orbitals, which is a non-degenerate state, and lambda 3, which is a degenerate band, doubly degenerate band, which are another combination of px and py and pz, which perpendicular to this combination of px, py, and pz, which is oriented along the 1, 1, 1 direction. Okay, so I'm going to double check this this picture here just to make sure it's right, but I think you understand the idea. From the band connectivity, you can get a sense of how the atomic characters of the different bands look like. Okay. What's also interesting, and group theory tells us, is about band crossings and anti-crossings, and what happens in some cases that we call accidental degeneracies. So, for instance, let's make a zoom into the band structure of aluminum, and you see that some bands cross. You see there's a band crossing here, and this is a crossing between a delta 1 and a delta 2, I think it's delta 2 prime band, and there's another band crossing here. This is a band crossing between delta 1 and delta 5, right? And this is interesting because we have talked about the degenerate states many times already in this course. And we have, most of the time, we have said that degeneracies happen whenever you have higher dimensional representations, right? But in this case, you see, for instance, delta 1 and delta 5. Delta 1 is a 1D representation, delta 5 is 2D. So whenever they cross here, it seems that I have a threefold degenerate state here. So, but this is not truly a degenerate state in terms of symmetry, but this is what we call an accidental degeneracy. Accidental degeneracies happen when two bands of different symmetries cross, and they can do that. There's no reason why they should avoid each other, right? Because they have different symmetries. When I block diagonalize the Hamiltonian, what happens in the block delta 1, the block delta 2 prime doesn't know about it. It's not gonna matter so to the other block. So it may happen that for some specific k point, these two states are degenerate, and so they cross, and this is what we call level crossing or accidental degeneracy. But when you have two states with the same symmetry, in this case two delta 1 states, you see that they never cross. So you can look here, there's a delta 1 band here, right? This is a delta 1 band, and there's another delta 1 band here, and you see they never touch, they never get close to each other. So if they actually try to get close to each other, what's going to happen is what I'm showing here in this picture. They will repel each other. So this is what we call level anti-crossing or band repulsion. This is also called band repulsion. So there was a tendency for these two bands to cross, but since they have the same symmetry, there is some mixture or hybridization between these two states, and they actually anti-cross, because this is forbidden. This degeneracy for two delta 1 states, since they are both one-dimensional representations, this is a forbidden cross, and that's why there's an anti-crossing here. So this is also called the level repulsion. So group theory tells us precisely what bands should cross and what bands should anti-cross based on their symmetries. Okay. All right. Okay, very good. So now we've seen the case of symmorphic space groups. Let's consider now the case of non-symmorphic group, and let's use it as an example. Let's consider the case of diamond structure. Diamond structure is a non-symmorphic structure. This is space group 227. Is a cubic symmetry, OH symmetry. This is the structure. Just keeping in mind that I have here black and white atoms, but for the diamond structure they should be the same. They should be the same atomic species. Okay, both carbon or both silicon or germanium. I'm just have different colors here just to indicate that they belong to different sublattices. Okay, which are separated by each other by this 1/4 of the cubic diagonal. All right. So let's see what happens at the gamma point. So some facts about the group of the wave factor at the gamma point. So the factor group, when I factor out the translations, is going to be isomorphic with the OH point group. The OH point group has 48 point group operations, but 24 of them are originally from the TD group, the tetrahedral group, the group of the tetrahedral, and they will exchange atoms within the same sublattice. They will take a black atom into another black atom. And the other 24 operations, the 24 remaining operations, I have to combine with translation, with the translation vector with this translation vector here, tau d, d from diamond, in which tau d is 1/4 of A111, in order to take one atom to another atom. So this one displaces one atom from one sublattice to the atom on the other sublattice. Okay? And these are, again, the character table for the group of the wave vector of the gamma point in diamond, in the diamond structure. You see that it looks pretty much like the same character table that we have seen before for a cubic group, Amorphic cubic group. The only difference is that you see here when we label the classes, we make sure that some of the symmetry operations, they include the translation by tau d. Okay? For instance, this one, this one, this one. So we make sure that when we write the character table for this group, we be specific about what are precisely the symmetry operations, which are compound operations that you must combine with the translation vector to take the crystal into itself. Okay. All right. So let's calculate the equivalence representation for this case. When you calculate the equivalence representations, the character for the equivalence representation, and we follow the rules that we have stated before, and we have to see which atoms are invariant under the different symmetry operations of the group. Okay? So in this case it's very simple. Why? Because I have only 2 atoms per unit cell, 2 atoms per primitive cell. So I can only have, and they are identical, so I can either have one of the 2 situations. Either the one atom remains in the same sublattice, and if that's the case, both atoms in the structure will remain in the same sublattice, so the character will be 2. Or if there is a compound operation that takes one atom from one sublattice to the other, then both atoms change, they interchange. Okay, there's an exchange between the 2 sublattices, and in this case the character is 0. All right, so the characters for the equivalence representations are going to be 2 whenever there is no translation, whenever there's a 0 here. So this is 2, 2, and it's going to be 0 whenever there is a translation here. So this is 0, 0, 2, 0, 0, 2, 2, 0. Okay? And you can then go ahead and decompose, and the result is going to be gamma 1 plus gamma 2 prime, or in the other notation, gamma 1 plus gamma 2 minus. Okay? So this is an example just to show you how you can construct the equivalence representation, or the characters for the equivalence representation at the gamma point. Okay, so let's explore a little bit now, going away from from gamma in a symorphic group, and I have briefly discussed this already today, but just let me go into that into more detail. So what this is, what we have to do now, if you remember, I have to multiply whenever I have a translation tau d, I have to multiply the characters by the phase factor. And the phase factor, for instance, this is for the delta direction. For the delta direction, the phase factor is e to the I k dot tau d. And if you have to remember that tau d is 8 divided by 4, 1, 1, 1. And k is a wave vector along the delta direction. Let me call it k delta. And k delta, or delta, it's along the kx, right? It's along the kx direction. So it's 2 pi over a kappa 0, 0. And kappa is a real number that goes from 0 to 1 when my wave vector goes from 0 to 2 pi over a. When I hit the x point, then I get 2 pi over a 0, 0. Right? Okay. So the dot product here is going to give me then the phase factor. And you see the dot product here, there's a cancellation of the lattice constant, and this I times pi over 2 times kappa. And this is why I have this phase. I'm reproducing this result here, right? This is the phase factor that we see in the character table. Okay? So this is how we go about understanding and calculating and using the character tables for non-symorphic groups for k different than 0. And there are other examples in the book, but I think this is sufficient to give you an idea. And if you need to use that for different directions and different points in the Brillouin zone, I think we will be able to do that. Okay? Alright, so this is it for today, and this is the end of chapter 10. There are 2 problems due next week, and once again I thank you for your attention.